Good morning everyone. Today we are beginning one of the most fascinating chapter of physics is wave optics. Before we enter into the details of concepts like interference, diffraction and polarization, we must understand the very important background, that's the dual nature of light. For centuries scientists debated whether light is a particle or wave. And Newton explained light is a stream of tiny particles which could easily describe reflection or diffraction. On the other hand, Huygens, a Dutch scientist, someone pronounced the Huygens, suggested that the light is a wave, which explained the phenomena like a interference diffraction. Later explained like a young double-slit experiment strongly supported the wave nature of light, while discoveries like a photoelectric effect proven the particle nature. So, light has a dual nature. Sometimes it behaves like a wave, sometimes also behaves like a particle. This is the foundation of the modern physics and quantum theory. Actually, in this chapter, we focus mainly on the wave nature of light, where we study the how wave interfere, diffract, and the Huygens principle and polarization. These phenomena cannot be explained the particle theory alone. Okay, so come to the whiteboard and we discuss the wave optics and Huygens principle. First, we study Huygens principle. Okay, so here, before we discuss of what is the Huygens principle, first take an example. When someone is throw a stone in calm water, and after throwing a stone like that, he's taken this example, picture taken example as an example. So stone actually hit the water, and after the strike, there's some generation of wave here, okay, and these wave are propagate, okay, spread out in or propagate in all direction, all 360-degree direction. These wave are in propagate in all direction, all 360-degree direction. Okay, it's look like there is a source point or this point. Okay, so after striking, these wave propagate. Okay, these are front line propagation. Suppose these, okay, and suppose and so on here. Okay, so we get these at top point. Okay, this top point I join from the way I join these. We get a circle. Okay, and this circle is called wavefront. This circle is called wavefront. This is a wavefront. This is a wavefront, primary wavefront. There is a secondary wavefront. Okay, and this is a wavefront. And say that there is a circle, all 360-degree. Yes. Okay, these are called wavefront. And very important concept is what is a wavefront. And if I joining the all these points, we get a circle here. Okay, we get a circle here. Okay, there is another direction, the side direction here, and there is direction these are. Okay, so they are all direction. In point on such a circle oscillating in phase. And keep in mind, these are the wave 1, these called wave 2, these are the wave 3. They all in same phase. Okay, they all in same phase. Okay. Okay, so they are oscillating in phase and they are the same distance from the source. Actually, this distance from this and this distance, these three lines, the same distance from the source here. Okay, and same distance from a source, such a locus point which oscillate in phase is called wavefront. So definition of wavefront in board exam is very important. Okay, you get 1 marks question. What is wavefront? This is a wavefront. Wavefront. Okay, so all points, write the definition, points on such a circle, these are the circle here, the circle are oscillating, or this also circle are oscillating in same phase, in a phase, actually there is no phase difference, but in phase, becomes they are same distance from the source. Okay, such a locus point, such a locus point which oscillate uh, in phase is called wavefront. Okay, so that's the wavefront definition is very important. Okay, so these are the wavefront, and you see that when they are propagated, and these wavefront, if there is some tiny particle here, and this tiny particle, a tiny dot, also create a source, and this source is called secondary source. These are the primary source, and these are the secondary source. These are treated as primary source, and there is some tiny dot here. These three tiny dots, 1, 2, 3, also behave as a source, and this source is called secondary source. Secondary source, and wave propagate in that direction. Okay, so if I draw another diagram for better understanding, so there is a primary source here, and these are the direction primary source, wave propagate in that direction. Okay, so the speed with which the wavefront moves, and these are the wavefront. Okay, these are the wavefront, and these wavefront after some time these get here, that's get here, that's get here, and wavefront are propagate. Wavefront are propagate in all 360-degree direction. Okay, so wavefront are not stay here; they are propagate and toward the outward direction from the source, and this speed of wave, and this is the speed of wave, and the energy of the wave travel in the direction perpendicular to the wavefront. Okay, if there is a wavefront, these are the wavefront, and these are direction of the speed. So actually speed here is perpendicular to the wavefront. So the speed the speed with which the the wavefront moves outward from the source. Okay, and these called speed of wave, and these called speed of wave, and there's the energy travel in the direction, and obviously there's a perpendicular direction. And now, and direction of the wavefront, and this is look like a spherical. Okay, if you have a point of source emitting from a wave uniformly all directions, see if these are uniformly in all directions, so the locus point which have the same amplitude or vibration here, so means these are the same amplitude or same vibration here. Okay, so the in phase obviously, so wave is known as a spherical wave, so this wave is known as a spherical wave, and in the large distance, okay, from the source, small portion of the sphere can be considered as a plane wave. So if I consider the small portion is called plane wave, and there is a propagation of there's a primary source, and these are the wavefront, and wavefront are look like a circle, and here we see that there is, when I say that, in a point in a wavefront is also behave as a source. Okay, so behave as a source. So when you see that these also behave as a source. Behave as a source. Okay, and this green color line is called wavelets. It's called wavelets. Okay, and these wavelets also, there is a direction of propagation. Okay, they are also direction of propagation. And now if I draw a tangent at that point here, if I, there's a huge number of wavelets, suppose there is another wavelet, there is some imaginary point, there is a huge point. If I draw a tangent here and join this tangent, okay, join this tangent, okay, these are the tangent in wavelets. Okay, and this tangent wavelets. Okay, and this get another wavefront, get a wavefront, and these are called wavelets. These green color line is as a wavelet, and these are the wavefront, and these called secondary wavefront. So, wavefront, and this is a secondary wavelet. This is called a secondary wavelet. Means the wavelet is a sort of like a source, and this is called as suppose as a primary wavelet or primary wavefront here. Okay, and these all points also behave as a source. Keep in mind, these are all points behave as a source. Okay, now keep in mind, okay, and if the Huygens principle mainly say that the essence is the geometrical construction of which given the shape of the waveform. So Huygens actually Huygens describe essentially geometrical uh, construction which given the shape of waveform, which given the shape of wavefront. Okay, and it is allowed to determine the shape of the wavefront is in later time. Okay, so here the mainly principle, the Huygens principle has said first all point and primary wavefront behave as a source. So first principle say that all points in primary wavefront behave as a source, behave as a source, and I see that, and these suppose after there is a wave here, and these are point, okay, point in wavefront is also behave as a source. Okay, and the second point we discussed the Huygens principle, the secondary wavelet, when all wavelets added to get a wavefront, added to get wavefront. Actually, first draw a tangent, so we get a wavefront, and this is a wavefront. we got tangent, we get wavefront. Okay, these two principles describe the Huygens principle. And if suppose you consider there is a suppose a source, a primary, there is a propagate. Okay, and here these point also treated as a source from Huygens principle, and they say that there is a treated as a source, and the direction of primary in that direction, but in secondary direction or all direction, these all direction are possible. So you consider that direction is secondary, and these are the primary. So there is some angle here, some angle is theta. Okay, so there is a secondary and there is a primary. So suppose these are the wavelets and these are the secondary wavefront. Because it creates these wavelets. Okay, these wavelets create a secondary wavefront. Okay, suppose I consider there is a time t when that from source to this point where wave travel, wavefront actually the wave travel from here to that point is time taken t. Wavefront travel from here to that point t, and these are the taken for small time delta t, and wave when that wavefront gets here, the time taken that is t plus delta t, and there is some angle here. So effect of the secondary wavelets. So there is another principle. Okay, and these are the effect of secondary wavelet JEE proportional to 1 by 2 1 plus cos theta. Actually that's not derivation needed, there's a keep in mind. Okay, the secondary wavelet effect of the secondary wavelet depending on the angle theta. Okay, cos of angle theta and 1 by 2 some concept here. Okay, that's the basic of the Huygens principle. Actually here Huygens described that movement and the wavefront. Okay, and you see that is a wavefront move here, not stay here, they move in all direction. Okay, and they are obviously the speed in that is the velocity, if I consider that is perpendicular to the wavefront. These are the wavefront. Okay, after some time these wavefront move here, and now the water in that point after source point, now here is a calm water, no motion here, but actually the wave travel these paths. Okay, clear. So now we discuss the reflection and refraction. That's two important points of a plane wave using Huygens principle. Keep in mind here we discuss only light as a treated a wave nature, not particle nature. Okay. So we discuss next point. Discuss refraction of a plane wave. Refraction of plane wave using Huygens principle. Using Huygens principle. And see the diagram, very important here. First we discuss refraction. So now we draw a refraction. Okay, so means there is a medium here, obviously a medium. Suppose the medium 2, that's a medium 1, and the wavefront, there's the wavefront. Okay, and there's a incident wavefront. There's the incident wavefront fall on this interface, suppose P and P dash, say that interface here. Okay, and suppose the density of medium 2 is greater than medium 1, so light travel from rarer medium to denser medium, obviously that's the wavefront. Okay, so now that's the normal here, so bend towards the normal. Okay, So now give the point name, that is a point, and draw perpendicular from this line from A to this line, that is B. Okay, and this angle be the I, and if suppose these are the 90 degree obviously, and this angle also be 90 degrees, so this angle be the I, incident angle, and this angle be the R, refracted angle. Similar name the point is these are the point B, and say this point's name is C, and draw a perpendicular from C to this line, and name point is D. Okay, and suppose this angle be the R, and this angle 90 degree, so 90 plus R, and this angle also be 90 degree, so so obviously that triangle ADC, and these are the exterior, PAD are the exterior angle, so PA, this angle 90 plus R, so sum of opposite of two interior angles, so that is 90 plus this angle be said, that is R. Okay, and the speed of light in medium one, one is a v1, that is a v2, and time taken be the same, that is tau. Here the time taken tau. For that distance, this distance b to c, that is distance equal to velocity into times, so velocity v1 times tau same, that distance bc, that is v1 tau, and AD, the velocity, that is v2, and the tau distance, tau time, so that is distance is v2 times tau, that's the AD, that's the BC. Okay, now discuss the triangle here ABC, the triangle ABC, that is a sin I, that is perpendicular. Okay, there is a 90 here, obviously there is a hypotenuse, that is the perpendicular BC by hypotenuse AC, and we take another triangle ACD, that is equal to the angle opposite a perpendicular, so AD is a perpendicular, that's the angle, so that is AD by hypotenuse, there's a 90, opposite of 90 is the hypotenuse, that's the AC. Okay, that is a sin R. And sin I by sin I, we get a Snell's law, that's why I apply the Snell's law, that's why I calculate sin I or sin R. Okay, so plane wave AB incident on the I, okay, there's a plane wave AB incident on the angle I, and the surface, that is the interface of PP dash of the surface at a medium 1 and medium 2, and refracted in CD. Okay, that is a refracted wavefront. Wavefront. Okay, and if that is a velocity, that is denser medium, obviously the velocity 1 is greater than velocity 2. Okay, and if I actually prove that with the help of Snell's law, the velocity. Okay, so from Snell's law, that is sin I by sin R, sin I by sin R, that is equal to, we get BC by AC, reciprocal AC by AD. AC cancel, BC, that is equal to V1 tau, that is V2 tau, tau with the cancel, that is V1 by V2, that is sin I by sin R, we get V1 by V2. Okay, and you see that I from small angle approximation, I obviously greater than R, so that is V1 greater than V2. Okay, so that the concept is the density in that denser medium, light speed of light is lesser than in vacuum. Okay, so ray bends towards the normal, so ray bends obviously rarer to denser medium, so that's the ray bends towards the normal. Okay, speed of light is decreases, so that is n1 refractive index of n1 medium, that is C by V1, and n2 refractive index of medium 2, that is C by V2. See the speed of light. Okay, and from Snell's law, that is n1 by n2, that is obviously sin n1 by n2, that is reciprocal of this sin r by sin I. So n1 sin I, that is n2 sin r. Actually there is a Snell's law, diffractive index formula here. Okay, so now introduce another concept, that's the wavelength. So there is some wave, obviously there is some wavelength, there is an incident wave, there is a wavelength, and there is obvious wavelength and frequency. So there is a wavelength lambda. Okay, so lambda wave 1, so lambda 1 represents the wavelength in medium 1, and lambda 2 wavelength in medium 2, and there's a length. Okay, lambda 1 is the length, that is equal to velocity into time, and obviously lambda 2 v2 into tau is the length obviously. So here lambda 1 by lambda 2, we get v1 tau by v2 tau. So tau will be cancelled, so v1 by v2, and we see that is a v1 is greater than v2, so lambda 1 is greater than lambda 2. Okay, so conclusion is that is lambda 1 is greater than lambda 2 means a more refracted here, so means more refracted. So now what is the frequency? So now I term what is frequency of medium 1 and medium 2. Medium 1 and medium 2. Suppose from formula, so we know that from sound chapter, that is frequency equal to velocity by wavelength. Okay, actually that is a wavelength equal to velocity by velocity into time, and that's the first one, 1 by time equal to velocity by lambda, 1 by time, that is equal to f, that's the v lambda, v by lambda. Okay, so see that very carefully. So if wavelength increases, so frequency decreases. Okay, and in case of medium 1, obviously the velocity also increases. So velocity also increases, so frequency also be that here increases. So that means frequency is not changed. Similar condition when wavelength is decreases, so frequency is increases, and if wavelength decreases means the velocity also decreases. So velocity is decreases, so means the frequency also be the decreases here. So now frequency be the same. So means that tau be the same, time taken be the same, so speed of propagation is decreases, but frequency remains same. So the rarer to denser medium, wave move from rarer to denser, so velocity is decreases, wavelength, the conclusion is that where velocity is decreases, so wavelength also decreases, but frequency remains same. Okay, that's the main conclusion of Huygens refraction chapter, refraction topic discussion. Okay, that's the diagram. So today in the class here I taken too much time. So if you have any doubt of refraction of a plane wave in Huygens principle, actually that plane wave using the Huygens principle, we discuss the refraction with the help of Huygens principles, and next class we discuss reflection with the Huygens principles. Okay, so if you have any doubt, please ask in comment section. I will try to give the answer. Okay, thank you for your time.